Okay, so we continue our discussion on gaseous detectors, and now we talk about drift chambers. The basic principle of drift chambers is that we let the electron drift through the detector, and we separate the drift and the amplification volume. So the sketch, let's look at the sketch to the right. There is a charged particle traversing the chamber and produces an ionization yield. We need a second detector to start the timing. This can be a scintillation detector, or if there is no scintillation detector in a collider physics experiment, another subdetector needs to provide a trigger. The drift chambers operate by means of measuring the drift time of the electrons. And to start that measurement, you need an independent timing measurement. So either that's a separate detector or from somewhere else in the detector. So drift chambers cannot be used for triggering because you need to know when the drift time starts. So let's assume that has happened. The particle has gone through. We have received the trigger. There's an ionization signal. Then the electrons drift through the drift volume to the anode wire. So they experience a homogeneous electric field in the drift volume. The electrons then reach the anode wire where the formation of an avalanche is triggered, an electrical signal is read out, and from that, the drift time, from the timing of that signal, the drift time can be measured. The drift time is simply the difference of T0 and T1, T0 being the trigger time or the timing provided by a scintillation detector, and T1 is the time we record the avalanche electrical signal close to the electron, close to the anode wire. So that's the main operation characteristics. It allows us to fill a large detector volume and still recover positional resolution, despite the fact that we only have a few anode wires, but the timing, the independent timing measurement supplements the missing spatial information. Drift chambers are therefore used in large volumes. Put two examples here. There are various possibilities to assemble drift chambers. In terms of the geometries, this is done. For one example, the bottom left shows a fixed target outer tracker, fixed target experiments, the Hera B outer tracker. So there's a fixed target collision somewhere happening here, and then there are magnets interleaved with drift chambers, and then there are tilted drift chambers to get two-dimensional measurements, and finally trigger chambers which have an independent timing measurement, so that they can also be used for triggering. Different pipes can be used for these chambers. It can be spherical or hexagonal. That's drift chambers consisting of pipes. One can also build, and these are large scale impressive detectors, cylindrical drift chambers with cathode and anode wires that are parallel to the beam. So here we have a large detector with anode and cathode wires running parallel to the beam. A magnetic field must be applied which by a solenoid magnet, for example, which will then be also parallel to the beam pipe and causing the bending of the particles, the tracks of the charged particle. This is a schematic example. In the transverse plane, it looks like this. There are anode wires and cathode wires. The anode wires is where the amplification happens. The cathode wires guide and provide the field. So when a particle runs through, one collects a signal, and from the timing of the signal at the various anode wires, a particle track can be constructed. We'll look at this a little bit more closely. Let's discuss a few realistic detectors. Here are the CMS drift chambers. The task is to have the electric field as homogeneous and the drift as homogeneous as possible, so therefore the drift velocity can be constant and known. These additional field wires that are put in place, for example, here between two anode wires, make the field homogeneous. Position resolutions up to 200 micrometer, as down to 200 micrometer for the large chambers, down to 20 microns for the smallest chambers can be achieved. The configuration of the CMS drift tubes looks like this. We have anode wires in a large spacing, and a fine grid of cathode wires put at the provide a constant electromagnetic field. These are small resistors making the potential a linear function of the z coordinate here in this case. And these many of these drift chambers are then assembled in one large chamber, and these large chambers are then what makes the CMS, what makes a large part of the CMS barrel muon system. So the rectangles here are the assemblies that hold the different drift tubes. Various gases are used to, and can be allowed. Various gases are used, and the gas mixture allows to distinguish the detector purposes. There are fast gases with a high drift velocity. These allow then high particle rates. Slow gases allow good timing resolution, a good measurement, and good control on the drift velocity, and therefore improve the spatial resolution. One can compare the drift chambers with the multi-wire proportional chambers. The advantage here is that one needs fewer wires. There's only a few anode wires that are read out for a given spatial or timing resolution. Therefore, with fewer wires, one can achieve higher precision, but if it becomes too low, the rate capability, of course, is reduced accordingly. In these large detector volumes, one always has the problem of electronegative gas impurities. So there has to be a way to recover and purify the gas during shutdown periods, for example. Here is an example of the a simulation of an electric field of a CMS muon drift chambers. It's 40 millimeters in length, a thickness of 11 millimeters. The wires are not shown, but you see that there's a fairly homogeneous electric field lines, and many of these muon chambers are then assembled in such a chamber in the CMS drift tube layout. Let's return to the cylindrical drift tubes with the wires that's schematically shown here. Let's look at what we can do with those wires. These are techniques that are used in the case of large, for the purpose of large cylindrical drift chambers, and more rarely for smaller ones. We want to do track reconstruction. Now imagine the transverse plane, and imagine the middle dots here would be our anode wires. So a particle goes through here, creates an ionization signal that is read out in the drift tube with certain drift times. Now there is a solution here, of course, if you reconstruct the track, but there's an independent solution that's mirrored at the plane formed by these wires. You don't know whether your signal came from left or from right. So there's always a twofold ambiguity if the wire configuration has a symmetry axis. This symmetry is usually broken to improve, to resolve that ambiguity. For example, in the transverse plane, the wire positions can be staggered, like shown here in the middle plot. Then you see little timing differences from one anode wire to the next, and the mirrored solution would not correspond to a straight particle track, so it can be excluded. That's one solution. Another solution is to tilt the plane of the wires, and a particle that originates from the beam spot, that would be down here, for example, would be a solution to the drift times according to the sketch here. The mirrored one would not point to the beam spot where the primary collision happens, and thus can be excluded. So these are two ways to remove the ambiguity in reconstructing a track from the drift times when you actually don't know, when you don't have directional information, you only have the timing information for the individual ionization yields. Another trick to improve the position resolution is to use stereo wires. It's a little bit hard to see in the top sketch, but one can displace a few of the wires on one side of the detector and not displace them on the other side. If you view this from the top, you would have the majority of wires running through. That's the C direction is the beam direction, and a few of the wires are displaced a little bit. Now this measurement, the timing measurement from the displaced wires, gives you some information on the Z coordinate. Usually those detectors are supplemented, these larger drift chambers are supplemented by other detectors which give a better resolution of the Z coordinate. But stereo wires is one way to resolve the ambiguity of the Z coordinate, because you really do not know where on the Z axis your particle went through. Here are a few images of realistic large-scale cylindrical drift shapes. The left one shows one of the largest ones of its time, the H1 experiment at Hera. There are 15,000 wires in this drift tube with a total force of 6 tons. The Bell 1 central drift chamber that's been removed from the Bell detector because it's now replaced with the one for the Bell 2. So here's a beautiful image. It has 50 cylindrical wire layers with 8,400 drift cells. These are large scale. These are the largest drift chambers that we built, and I think they are beautiful detectors. Now, they are also dangerous beasts because if one of those wires is damaged and rips, whole segments of the detector will be destroyed because the wire will shortcut a great many of channels, and one loses then whole segments, and would have to disassemble the whole detector and repair that, which is not economical. Hence, there are security factors built in that this cannot happen, so the wires are thicker than they need to be, and so on. So it's a large-scale project that scales very non-linearly to build such a detector. Since we are talking about very large detectors, let's also talk about time projection chambers. Time projection chambers are gaseous detectors. They fill very big volumes with gas. There are no wires in the main volume. On both, so we have in the middle a central cathode of 50 or so kilovolts. I think I took the numbers from the Alice TPC. We talk about 5 meters of diameter and 5 meters of length. So these are enormously large single detectors. There's a drift gas in that's filling the volume, and there's a central cathode at minus 40 kilovolts. Now, in the left half of the detector, the electrons that are created from the ionization drift to the left, and on the right side, they drift to the right. At the end of these detectors are readout planes. These are multi-wire proportional chambers with segmented cathodes. So imagine you have a spiraling charged particle. It spirals because of the magnetic field that you apply by means of a toroidal, or, for example, a toroidal magnet. Now, there will be the charged particle's track will bend. It will give a segment of a spiral in the gaseous medium, and that will drift with the electrons will drift with kilometer per second, as we've said, kilometer per second speed towards the readout plane. At the readout plane, we have anode wires and cathodes. At the anode wires, this ionization signal will trace out a projection of the spiral in the 2D plane, and by measuring the timing of the amplified signal at the wires and at the cathodes, we can, in fact, from the timing information together with the two-dimensional information, one can fully reconstruct the three-dimensional event. So the third coordinate is thus deduced from the time of the arrival of the electrons on the anode wires. It is, of course, a very difficult detector to operate because one needs to make sure that the ions that are created in the amplification at the anode wires do not propagate back into the drift gas, because the drift gas is the sensitive material. It should be ionized. It should not be full of. It should be. it will be ionized, but it cannot be full of, it should not be populated with amplification ions, because those could recombine with the electrons that go the other way. So there are gates here that stop the ions and absorb these, and the gates potential needs to be timed to the collisions that happen somewhere in the center of this detector. So the whole process is as follows: you have a collision with tens of thousands of tracks traversing the whole volume, ionizing, well, producing ionized tracks that are then, with kilometer per second speed, projected on the anode wires at the segmented cathode, which allows to get the timing information with the positional information to give a three-dimensional image of the event. And while this and then close the gate to absorb the ions from the avalanches that appear at the anode wires. It's a miracle that such a thing actually can be successfully operated. Here is the LH-TPC, which is the largest example. You can see in the sketch at least the readout chamber. It is a toroidal detector. It can tolerate extreme occupancy, higher occupancy than any other subdetector. It's ideal for heavy ion collisions that produce such particle multiplicities. However, because of the large detector volume, and although it's a kilometer per second drift velocity of the ionization signal, the electrons, you still have hundreds of microns dead time. It takes a while to read out this detector, so it cannot, with 280 microseconds, it cannot operate, of course, at the LHC bunch frequency of 25 nanoseconds. The detector would be constantly lit up. It can be operated with 3.5 kilohertz. The inverse of that frequency gives you the maximum time between two collisions that can happen in the detector. However, the information that is read out is so enormous that actually the bandwidth of this detector is limiting to 300 hertz. The gas that's used in the LH-TPC is neon CO2 mixture. However, actually, I know the guy who operates this, one of the guys who operates this. Our children went to the same kindergarten when I spent time in CERN, and they frequently tune and change the gas parameters, and the gas, which is always a highly critical endeavor, because if you have impurities there, you cannot operate. You can, of course, not operate this, and if something goes wrong, it means weeks of repair and recovery. Neon is used to reduce the multiple scattering because it is a very large detector volume. On the other hand, it's okay to have only 40% or so of the ionization density of, for example, argon that could also be used. So here one opts for a smaller ionization, and in turn has a better handling of a lower rate of multiple scattering. This is what the LS-TPC looks like. The TPC is outside of this guy. It's a toroidal apparatus. These are the last few pictures from inside. As you can see, the field cage. And this is what an event looks like. I think it's really incredible that this can be achieved. This is the left is an event display. We looked at it before. It's an event display from lead-lead collisions at 2.36 TeV, the track occupancy is staggering. If you imagine that half of the tracks are projected on one side and the other half of the tracks is projected on the other side, with timing measurement and multivariate proportional chamber measurement in a 2D plane extrapolated back. That this all works is a significant achievement. There are, of course, other subdetectors, in particular time of flight detectors and tracking. And thus together per particle, we have a momentum measurement and a DEDX measurement. And if we show the momentum versus the DEDX, we see the different populations from the different particle species. So if the momentum is not too large, we can read off from the EDX which particle it is. Here it's shown for antimatter electrons, so for not antimatter, for negatively charged particles. E minus, pi minus, anti-kaons, antiprotons, deuterium, and antihelium, antihelium-3 and antihelium-4. And I think we had, I highlighted this the other time, we had 10, I think 10 antihelium-4 nuclei. These are the only detectors where we can do 3D reconstruction of the whole track. There are many measurements per individual particle track. It only depends in principle on the segmentation of the anode and the cathode in the readout planes. So these are TPCs. They are rarely used, but beautiful and interesting to discuss. In terms of history, to give you an idea when these were invented, the multivariate proportional chambers are from the late 60s with drift volumes in the millimeter range. The drift chambers not long after that separate the amplification region and the drift region. In 1969, Chapag was involved again. And then the time projection chambers with meter-sized drift volumes in the late 70s and 80s. A few issues related to detectors with wires, although I mean a TPC, most of the detector is empty, however, wires play an important role in the readout, and not only TPC, all wire detectors need to be typically operated for decades, or at least a decade, and you cannot disassemble them. It's easier to build a new one. So it's important that the operation is stable over many years, and that's not at all easy. The avalanche formation can be considered like a little bolt of plasma. There is a plasma discharge close to a metallic surface, which can trigger all sorts of chemical reaction at a small rate. But if the occupancy is high and after a long time radicals can form, then polymerization can happen. You can see that, for example, at the bottom left. Now, that's certainly a few microns thickness here, which would really change the electric properties across these wires that have to be taken into account when calibrating the readout of this detector. The polymers, in particular, if organic gases are used, can attach to the electrodes and reduce or change the gas amplification. The contamination, of course, must be avoided. These are large assemblies. There's different kinds of metals and plastics involved, and oils and fats, and all these may leak into the gas, which ideally can be purified, but will always be present at a low rate, and that rate has to be kept to sustainable levels. So you can see in these pictures here what happens to wires if operated in this very high electrical field strength close to them in a gas with avalanche formation over decades. It's best to not have wires. Wires should be avoided or can be avoided, or in recent years, much of the effort in developing gaseous detectors went into avoiding wires altogether and combining the advantages of semiconductor detectors with the advantages of gaseous detectors. So have high granularity in a high volume. So let's talk about micro-pattern gas detectors. This is an overview. This is an overarching concept. There are several detector concepts under this umbrella. The main task is to separate the hits of particles at high rate experiments, which require a high granularity in these sub-detectors. Now, in principle, you want to make your detector smaller, but that does not work with wires. Wires cannot be made arbitrarily small. The smallest wire diameters are 10 microns, and then unit spacing. Micro-pattern gas detectors do not have wires. Instead, the electrodes are material that's printed on the structure. There is therefore also no risk of catastrophic damage from broken wires. I mean, there's other catastrophic damages that's possible, but well, there are no wires around. One can use photolithography to print the structures on supporting material, and there's industry technology to facilitate that. Because there are no wires, there is more flexibility in the detector geometry. And one can also make the cell size smaller. Position resolution can easily go down to 30 or so micrometer. That's hard to achieve, possible, but hard to achieve with wire detectors. The rate capability in turn is very high. We talk about megahertz per square millimeter instead of, for example, kilohertz. So one can move those detectors much closer to at the same rate, or one can have simply fewer of those and tolerate higher rates. Because typically micro-pattern gas detectors occupy smaller volumes, that's what they're designed for, the gas should have a high primary ionization yield. For example, DME is a gas that's often used. Let's look at the comparison of the rate tolerance. This is a characteristic comparison of a multi-wire proportional chamber and a microstrip gas chamber. We'll discuss next. Microstrip gas chamber is an example of a micro-pattern gas detector. If hits in the detector accumulate and you can no longer separate them, the individual gain per hit reduces. So if above a rate of 10,000 per millimeter squared per second, the multi-wire proportional chamber begins to give up. The microstrip gas chamber can tolerate rates that are 2 orders of magnitude higher. So here we have megahertz per millimeter squared per second. We look at microstrip gas chambers. These are the MSGCs. gas electron multipliers, and micromegas. The ideas are simple and similar behind the three. Still, I think it's an ingenious use of technology that's available in the industry. So we start with microstrip gas chambers. Here we have amplifying anodes and cathode strips etched on a substrate. The substrate can be glass, ceramic, and plastic. The gas volume is only a few millimeters. Here in this example, in this sketch, it's 3 millimeters. There are no wires. You see anodes, 5 microns, and cathodes, much larger, 60 microns, in a spacing of 100 microns, and a substrate and the backside electrode. The resolution is 30 microns in this simple assembly, which is 10 times better than typical multi-wire proportional chambers. The trick is that the cathode, so here we have an anode and a cathode next to each other. The trick is that the cathode improves the field geometry and collects the ions from the amplification. So we have a particle going through, as usual. We create electron-ion pairs. The electrons drift to the anode and cause avalanches, and the ions from the avalanches are absorbed by the cathodes, and at the same time, as you can see at the right-hand side, the field lines close to the anodes are changed by the cathode voltage such that the drift of the primary ionization electron signal is channeled towards the anode, because the cathode pushes a little bit away, of course, the electrons and channels this towards the anode. These detectors are extremely simple to assemble. You need the cathode and the anode that comes out of the acid bath where these structures are reached, and then you just glue these together. In this way, one can also, at the same cost, one can instrument large detector volumes when compared to gaseous detectors with wires. There are problems here, of course. One of the problems is that you have large voltage differences at the 100 micrometer spacing. So typically, these can be hundreds of volts here at the 100 microns. Of course, in principle, it's no problem to calculate that this is safe for operation. However, sometimes a highly ionized heavy particle can come along. Think of, we have violent reactions happening in all these detectors. Sometimes a nucleus can be fully ionized, and I don't know, maybe a carbon nucleus with a large C squared may traverse between the anode and cathode and fully ionize the gas, and then they can trigger a disastrous discharge, a shortcut. That can happen by single, highly ionizing, heavy, probably slowly moving nuclei. Remember that Bethe-Bloch tells you the ionization energy is proportional to the C squared of the heavy particle. And you can, if it's iron, you have 56 squared is a large number, gives a huge ionization channel that can lower the resistance such that the catastrophic discharge can happen and shortcut a few wires. Nevertheless, if the environment can be controlled enough, these are still very interesting detectors. The next step that avoids that problem is the gas electron multiplier, or GEM. This is a novel detector concept, I think, developed actively developed, is still actively developed, was major development happened in the last 20 or so years. It's an interesting detector concept of very simple components combining safety with technological feasibility. It has a very high radiation resistance in contrast to the example we just had, where it's actually dangerous. Here we have a very high radiation resistance. So what's the trick here? Again, we separate the drift space from the amplification space. That's the whole idea. That's also important for the microstrip gas chambers. We have drift space and we have amplification space separated. Now here, the separation is facilitated by the so-called gem foil. The gem foil is a very thin foil, 50 micrometer in this example, that has a pattern of holes. The holes are spaced in tens or hundreds of micrometer, in this case 140 micrometer spacing. And what happens? You have a particle going through, causing an ionization signal. The ionization electrons now drift towards the foil. The foil is at a high, the top and the bottom of the foil are on a high relative potential. So there's a large voltage applied between the top and the bottom surfaces. That means there will be an enormous electric field gradient inside these holes. And that's where the amplification happens. So you have typically you have a thickness of 50 or so microns. Voltages can be hundreds of volts, which means we are way above the voltage threshold for secondary ionization. And if an ionized electron, if an electron from the primary ionization signal comes along, it's channeled through one of these holes, and here it amplifies. You can see this maybe better in this sketch. And then the avalanche amplification happens only in this region, and then those amplified electrons drift towards the readout board, where we find again anode and cathode strips exactly equivalent to the previous case. This gem foil in the middle is cheap to build. It's metallized on both sides so that we can put it on the voltage, on a high voltage difference. However, it's of course the top and the bottom are insulated from each other. 50 or 70 micrometer thickness is a usual thickness, because you also want mechanical stability. 400 volts can be applied, and this gives us an amplification of 10 to 100 maybe. Now 10 to 100 is not a lot. However, we can have several of these gem foils on top of each other, and that's what's done. So practical detector applications have, for example, triple foils. And with triple foils, we are in the 10 to the 4, 10 to the 5th amplification regime. And so that's enough to detect single particles. Remember, a single particle can be detected if we can achieve a production of roughly 1 femtocoulomb. 1 femtocoulomb is 10,000 electrons. And with a factor of 10,000 to 100,000, we can do that. The crucial idea, so in summary, for the gems is that the amplification only happens in the holes inside this tens of micrometer thick foil. Micromegas is the last detector concept we discuss. It is similar to gems. It is even simpler. It stands for micromesh gaseous structure. it also separates the ionization regime, which is typically 3 millimeter, from the amplification region. The amplification region is 100 microns. The microstrips are at the bottom. There are, however, only, this is only anode, so it is not as dangerous because we do not operate anodes and cathode strips close to each other. So we have microstrips at the bottom. There is a simple gate here, the Mikrogitter in German, and the spacing is again in the tens to hundreds of micrometer regime, and it is put at a voltage such that we have a drift electrical field of 1 kilovolt per centimeter. Here we optimize the drift velocity, and we make the detector thick enough so that we can accumulate a large enough ionization signal, and then a voltage is applied so that we have field strength of 40 or so kilovolts per centimeter, which is then used for avalanche formation for secondary ionization, so that we can actually read out the signal from individual particles. 100 or so micrometer spatial resolution is achievable. The main advantage here and in all these detectors is that these can be homogeneously integrated with CMOS pixel readout chips. So one can develop sensors and have detector assemblies that are seamlessly integrated. Micromegas is, for example, used in the tracking in the compass experiment. Okay, in summary, I put here a few numbers. This is from the PhD review from 2017. We have discussed many of these detectors. We're going to discuss still silicon strip and pixel detectors in the next lectures. Spatial and time resolution is what is compared in this table. So RPCs, resistive plate chambers, don't have very good spatial resolution, but nanoseconds timing resolution. The proportional, the drift, and the micro pattern chambers do much better. In particular, the micro pattern chambers do much better in spatial resolution. So they are the tool of choice if spatial resolution if high spatial resolution is required, for example, for tracking. Otherwise, the timing resolution is in the nanosecond regime. Now, as you can see here, the silicon pixel we can achieve below 10 of micron spatial resolution, and also in the nanosecond regime. So silicon detectors and these advanced gas detectors are the two, let's say, main detector concepts that are used when assembling large experiments when it comes to the collection of ionization signals for particle identification. The other big group of detectors are, of course, the calorimeters. Good, there's a lot I've not discussed, of course, because they are special purpose. One can build liquid argon, liquid xenon, even drift chambers. One can build bubble chambers. These are a thing of the past. The liquid argon drift chambers have to tolerate a low occupancy. They can be used to search for highly energetic neutrinos, for example. And then we have nuclear emulsions, which in fact were used to discover nuclear spallation, but with the high statistics experiments that we're dealing now, those can no longer be used. And that's it for the gaseous detectors. We now start with silicon detectors. I stopped the recording.